In 1921, a scientist goes by the name Brandel published the result of his study on the penetration of hard bodies, such as metal bunches into a soft material. This theory became the base used by other scientists called Terzaghi to determine the ultimate bearing capacity of the soil. Whenever we say there is a theory, that means there are assumptions formulate that theory. Terzaghi assumes that the foundation is shallow. In mathematical terms, that means the depth of footing is less than or equal to its width b. He also assumes that the ratio between the length and the width is more than 5, and that's what we call a strip footing. He also assumes that the weight of soil above the base of the footing is replaced by a uniform surcharge equal to gamma times dF. He assumes the soil will fail under the general shear failure, which we explained in the previous video. To understand any theory, you need to define the loads affecting the model. We explained that under the general shear failure, we have three main zones. The load coming from the column or the superstructure will transform into a uniform pressure that ultimately will cause the failure. This load will cause two types of stress failure. The first one will be the shear stress, which depends on the cohesion of the soil. The force coming from the shear stress in this case will be defined as the force required to break the cohesion between the soil particles. And to calculate this force, you need to know the angle of the friction failure and the coefficient of cohesion. And that's what we call in the basic soil mechanics the shear parameters. The second force will come from the normal stress resisting the zone 1 from falling down. This forces is a combination of three forces. The first one is the passive air pressure coming from the weight of the triangular wedge. The second is the cohesion force, and the last one is the surcharge resistance. To understand these forces, we need to go back to the concept of soil mechanics. Imagine if we had a retaining wall placed next to the soil. The effects of the soil on the retaining wall will be defined by three conditions. First, if the wall has minimal to no contact with the soil, we call this condition the soil at rest. If the soil moves towards the wall, the stress that develops would be referred to as active air pressure. If the opposite occurs, meaning the wall moves towards the soil, this is referred to as a passive air pressure. To estimate this force, a scientist who went by the name Rankine developed a theory in 1870. In a simple way, he stated that the horizontal or lateral stress on the soil will be a function in the vertical stress. To understand that more, let's consider the hydrostatic pressure in the water. The horizontal pressure at any point will be equal to the vertical one, which depends on the depth and the unit weight. If we apply the same case to the soil, we will find that the horizontal stress will not be exactly the same as the vertical one by a factor called the air pressure coefficient, which will depend on whether the soil is in active or passive state. And since the resultant force coming from these stresses will be equal to the area of the shape times the specific weight gamma, the force will be equal to half times h times k h gamma. We can expand on this subject in the future, but now let's go back to our main problem. We can imagine zone 1 like a retaining wall moving towards the soil. In this case, the soil will be in a passive condition. So the force coming from the passive air pressure will be equal to the one we explained before, except the K factor in this case will be different. The second force is cohesion resistance, which is the vertical component of the cohesion, and this force will be uniformly distributed around the zone. And lastly, we have the surcharge contribution, which will be uniformly distributed around the zone as well. Now let's do a load balance. In downward direction, we have the load coming from the footing and the weight of the zone. In the upward direction, we have the passive resistance for the soil weight gamma, cohesions, and surcharge, in addition to the vertical components of the shear force. This force will equal to the Q times the area, which will be the footing width B times the third dimension. You can assume that third dimension equal to 1. The weight of triangular zone will equal to the unit weight times the wedge area, which in this case will be equal to half multiplied by the width B multiplied by this length, and let's name it h. And since tan phi in this case will equal to h over b over 2, we can arrange that to find h equal to b over 2 tan phi. So the area will be equal to half multiplied by b over 2 tan phi. That could be written as 1 over 4 b square multiplied by tan phi multiplied by gamma. The shear force will be equal to cohesion times the area. This links, and let's name it z. And since the cosine phi will equal to b over 2 over z, as a result of that, the z will equal to b over 2 over cosine phi. So the shear force will be equal to 2c multiplied by b over 2 over cosine phi. And to find the vertical components of this force, we have to multiply this by sine phi. The passive resistance will be divided into 3 components as we stated before. The passive force resists the weight. Let's name it B gamma. And the passive force resists the cohesion, and let's name it BC. And finally, the passive force resists the surcharge, and we name it BQ. B gamma will equal to half times gamma times h square times k gamma. BC will equal to C times HKC. BQ will equal to Q times HKQ. The combination of load will look like this. Let's arrange every term that have gamma alone. And let's do that for every term have C and Q. This term has been named NQ by Terzaghi, and this was named NC, and this is N gamma. NQ, NC, and N gamma are known as the Terzaghi bearing capacity factors, and you can notice that every one of them depends on the pressure coefficient and the angle of friction failure. You can find a table for this coefficient based on the angle phi. Terzaghi's theory has been expanded by the many scientists to be applicable to the circular footing and square one. Also, some modification has been applied to the equation to make it suitable to the local shear failure. If you want to know the difference between the failure mode, you can watch this video. In the next video, we will talk about the effects of the groundwater table on the bearing capacity. If you have any question, leave it in the comment down below, and I will get back to you with a satisfying answer. If you find this video helpful, you can like, subscribe, or even spread the word. Also, the reference we used will be in the description down below.